Thank you so much. This is the last session, so you are tired, and my colleagues did a great job to make it easy for me and for you as well. So this work is done by Weifang. He's a PhD student in the CSE department at Chalmers University, and his supervisor, Ahmed. So a quick question here. Do you know what is this? This is Status of David. And he has been, the artist who made it, he has been asked how he made it. And the answer simply was, he just removed everything that is not David. And probably you are wondering, how is this relevant to this paper? And the key aspect here, this paper is doing software debloating for machine learning frameworks by removing any unneeded code from shared libraries. So as you all know, software is growing, but developers are keep adding more features, and this will add more code. So the size of the code that is added to, for example, to PyTorch, around almost around 500,000 lines of code. We have people here from PyTorch, they can confirm that. But if we can take this as an exemplar, we can see there is a tremendous growing. However, this growth in the code by adding more feature leads to the issue of software bloat, which is defined as unnecessary code in the form of unnecessary features or a large size libraries that incorporated in your code. And according to prior art, they define, or they came up with the classification for software bloat. The first type is bloated that universally can be removed. You can think about that, about this like dead code, so you don't need to remove any features. And the second class of software debloating, software bloats, is the customization, where you have some use cases, as we have seen in the previous talk, there are some customization or some custom workloads that you need to execute based on certain architectures. This means you need to do some sort of customization and removal of unnecessary features. And this paper is focusing on the second class, which is type 2 bloat. So now if we talk more specifically about machine learning frameworks, if we take, as you know, TensorFlow, PyTorch are the core of machine learning systems. And they are cooperating and written in languages like C++, CUDA, and Python. And ultimately, the binary size of those libraries end up in a huge size, which is making it difficult to run it on edge devices and mobile devices. And shared libraries plays a main contribution towards this issue. That's why this paper is focusing on debloating shared libraries for machine learning frameworks. So in a prior work that I was involved in, we studied this issue between traditional application and machine learning applications. And we found that shared libraries in generic applications around the size between 2 meg and 30 meg. But when it comes to machine learning shared libraries, the size moves to 200 to 1200 megabytes. So you can see that the size of shared libraries in the context of machine learning application is really large. And what is also another, you see, a unique aspect about shared libraries that are used in machine learning frameworks, they incorporate both CPU code and GPU code. Unlike generic applications or traditional applications where you have only CPU code. And in fact, the authors studied the percentage of CPU code and GPU code in machine learning shared libraries. And they found out the size is between 68% and 91% for the shared libraries in machine learning frameworks. As you can see here in this plot. So in contrast to CPU code, this represents a small fraction of these libraries. So the gap that the authors are trying to address here is that bloated CPU code has been previously studied. Also in this paper, if you go to the last section, the material section, they also proposed CPU debloating. They call it negativia. So, but the bloat has not been explored well in the domain of machine learning GPU code. So the challenge that here the authors are trying to address is some machine learning shared libraries are not open source. So this is the first challenge, so that they don't have access to the source code. And the second challenge, it's, as I mentioned earlier, it's underexplored area, and the structure of GPU code is different than the CPU code. So now here we will discuss how negativia ML, this is the GPU debloating version of their approach, negativia ML. Here in this workflow, we see in action how it works. First, you have you train the model based on PyTorch. The first step is called kernel detector. So in this step, the authors are trying to identify what are GPU kernels that have been activated. And then in the next step, the kernel locator, the authors are trying to identify among those kernels that have been accessed, which are the files that are used and unused, so they perform the removal process. So let's talk first about detecting used kernels. So first, CPU launches kernels, and then the CPU launched kernels may or may not launch other kernels. And the kernel launched from another kernel is called GPU launching kernel. These kernels form a call graph that is called kernel call graph, where the start of the graph is the CPU launching kernel. And by monitoring the CPU code, the authors can identify CPU launching kernels and subsequently consider them as used. So this allows the authors to detect used kernels without the need to do GPU level monitoring. So let's continue on that example. If we see here for detecting used kernels, based on the observation, kernel detector hooks the function cu module get function, and it extracts its input. And this inputs will indicate the kernel launched from the CPU. So for example, in this, when you train this model, it invokes kernel matrix multiplication. The CPU code must call the cu module get function, and the kernel detector will get the inputs, which is the name of the kernel. Note that the CPU launching kernel may also launch other kernels on the GPU. Kernel detectors cannot detect such GPU launching kernels. Now moving to the next step, after detecting the kernels that have been called, now is to identify or to locate the file range used on that kernel. So to do this, negativia ML does the following. So it analyzes the structure of the GPU code according to the CUDA documentation manual. The GPU code is organized as follows, as we can see here in this figure on the left side. So basically, GPU code consists of a set of regions, and each region consists of a set of elements, and each element contains the kuben, basically the part that contains the code, the GPU code, and the element header. So what it does here, for each Kuben, the author extracts the kernels included in it. If Kuben contains a used CPU launching kernel, the whole Kuben needs to be returned. So how about GPU launching kernels? So what they do here, if the kernel is launched by another kernel, the two kernels are compiled into the same Kuben. It means by returning the whole Kuben, the whole kernel call graph is also returned, including the GPU launching kernels as well. If a Kuben matches the GPU architecture and contains the CPU launching kernels, then the authors retain the Kuben, and the other Kuben are removed. So now for evaluating the approach, the authors here used 4 popular machine learning frameworks like PyTorch, TensorFlow, VLLM, and transformers with different models and modes of operations, like training and inferencing. So now the first part of the evaluation is identifying Bloat, the main sources of Bloat, and the reduction that they can achieve. So the numbers between round brackets represent the reduction percentage, either for CPU code or for GPU code. So you can see here the tool achieved around 66% reduction. Also, you can see here the amount of code that is contributed by CPU and GPU code. And as you see here clearly, the majority of the size of the code is coming from GPU code. So 80% of the GPU code are removed due to mismatch of GPU architectures, according to the observations made by the authors. And they identified 2 reasons behind this observation. The first one, the Kuben does not match the GPU architecture. And probably this is relevant to the previous talk where when you have different architecture, you will have lots of code that are not relevant to that architecture, so you need to customize it. And the second reason is the Kuben matches the GPU architecture but does not have any used kernels. So the second reason is coming from the unused features or unused kernels. So in conclusion, most of Kubens are deleted because the mismatch of the GPU architecture. And software bloat can stem from hardware. So now the authors evaluated also the influence of different workloads on the functions that are used in the shared libraries in the machine learning frameworks. If we take an example, Torch CUDA shared library, it has been evaluated based on 6 different workloads, based on the 3 architectures, PyTorch, VLLM, and transformers. And the authors collected the functions that have been executed or used, and they found out 77% of used functions are same functions. So this indicates that different workloads used a lot of common functions in the library. And now the final aspect about the evaluation, which is the runtime. And also the authors identified the memory and memory usage for CPU and GPU code. So you can see here the reduction achieved for CPU code around 75% and for GPU code around 70%, which is a great reduction in the memory consumption. And the execution time, they achieved a reduction by 44%. So on average, across all workloads, CPU, memory, execution, the reduction was around 2 giga 2,500 megabytes and 443 megabytes and 2.6 seconds. So in conclusion, in this paper, the authors propose negativia ML to debloat both CPU and GPU code within machine learning shared libraries. Negativia ML is the first tool to specify to specifically address GPU code bloat in ML libraries, and they evaluated negativia ML thoroughly by over 300 shared libraries. And the bloating ML shared libraries reduced, according to the evaluation, reduced the file size, CPU and GPU memory usage. And it's also improved the loading performance. So the authors are interested in extending this work, and they will soon open source the code. Here is the QR code. I don't think they released it, but here you can access the repository. And if you have any questions, we have the author now with me. It's now almost 3 a.m. in Sweden, but they are happy to answer your questions. They both are here. And also, you can contact them if you have any questions also. By the way, just lastly, Weifang is also in the job market. I don't know why it sounds... Okay. I think this is the most important part. Anyway,
let me see that.
It does not show the last slide, but Weifang is in the job market. He's looking for internship.
Yeah, thank you for a nice presentation. I have a quick question about, say, there's a famous saying, everybody is using 5% of a software, but different people are using different 5%. So in this case, do you think, is there like any take the vendors should have like to reduce the library size, or there is basically nothing they can do, but like users can use this to deploy on their system? Is that clear?
Ahmed Weifang, have you heard the question? Have you heard the question?
No.
Can you repeat the question, please?
Okay, yeah, like I was saying, like there's a famous saying, everybody is using 5% of the software, but different people are using different 5%. So like from a vendor's perspective, what they can do to mitigate this problem, or is basically the users has to deploy tools like this, like locally to improve the performance.
I think I get the question. So if I will repeat the question to see if I understand it correctly. So the question is that so different users use different part of the software or of the framework. So if you develop some part of the framework, so it might break the other use case of the other users. Is this the question?
Yes.
Yes. This is a correct question. So the problem is that, so nowadays, the software development process, not only this is not limited to machine system or machine framework, also applies to general software. Is that the library or the framework developers, they want to provide a more general framework, more general library to the users to cover as many use cases as possible. But for the users of the library, so they usually use only a part of the library or the framework. So there's a gap actually between the library developers and the library users. But for the library users, actually there are options to stop this question. I only use like 20% of these features, but I need to include all these library, all the code in my software. Their solution to this problem is kind of very limited. According to nowadays, the software development process, they're very limited. They either compare the framework, like a PyTorch framework, or maybe other frameworks from the source code to do some customization, or maybe they choose, maybe they even choose other frameworks that meet their use case more precisely. But these solutions are quite limited, and sometimes it's not even feasible. For example, as a cloud provider, you allow users, the cloud provider allows users to upload their own, like maybe serverless functions. The user can upload they build their functions, using their own PyTorch framework their other frameworks. But as the cloud providers, you cannot say, okay, you need to compare your framework from source code. It's not possible. So I would say this, by our approach, it's kind of we provide a solution, at least provide another solution to the users to specialize the framework according to their own use case.
So
I hope this answers your question.
Yeah, before the next question, so this session is officially finished. So if you want to leave for reception, feel free to go. But because this is the only opportunities for people to interact with the authors, so I will be here and feel free to ask author any questions when they are 3 a.m.
Hello. I do have a question. I guess I actually get your point. The called Via Negativa. I guess that's how you get the name. But my question is, when do you observe diminishing benefit for cut off the redundant GPU code? Because when you have a huge models, let's say I recently just downloaded the DeepSeek full-size model, which should be 600 gig-ish, and that is a huge. So compared to the huge parameter size, the code itself are becoming less and less important. So like maybe you are running MLSys, the huge framework will be or like too heavyweight. But if you already have a huge model, it won't be that important. So I'm curious, have you observed, is there any cutoff line or sweet point for GPU code and the actual model?
Yes.
If you understand my question right.
Can you please bring back the slides, the table where we have the runtimes? I think this is a great question. We actually have this in the evaluation. So if
I think it's
Which table?
page 21. I think it should be page 21.
Okay.
Yeah. So for the large models, actually the memory reduction is not that is not as good as the small models, because for large models, the model itself, or we call it data.
Yes.
That part occupies the most of the memory instead of the code. So by this code debloating, we only remove the code. So if the data part occupies more memory, so the relative reduction will be less. That's the answer. Yeah.
Okay, got it. Thank you.
Yeah, hi. Thanks for the work. I think this is very interesting, and I do have a more kind of a technical detail question. So, I see that you can cut off kernels, right? But in CUDA, there's also CUDA module, which might including more than just one kernel. So, for example, let's say I have a CUDA module that including 100 kernels, and you are only using 2 of them. Is the work that you've done currently is able to pull out those 2 kernels and repackage them into a single CUDA module and eliminate the old one? Or right now the tool is only operating at a kind of a cubing level?
I'm not sure if I understand the question correctly, but for the GPU debloating part, actually we are not removing the kernels. Actually, we remove at a higher granularity. We remove the cubings as we have shown before. So because we don't know the exact structure of the GPU code, so we remove the cubings. So if the cubing include use the kernels, so we will retain the whole cubing. And if the cubing does not include any used kernels, so we remove that cubing. So it's not remove the specific kernel.
I see.
So it's more like a
yeah, but it's
higher granularity.
Let's say if in the kubing can including more than one kernel as well, right? Like, so if in a
Yeah,
kubing there's
yes.
one kernel being used and one is not, then you will be repackaging the kubing, or you will just keep the whole thing?
Repackaging. So we don't do repackaging. So
I see, okay.
after remove, so basically we don't do the repackaging. You don't need to repackaging. So the tool works like this. So you run some workloads, then it will generate the specialized libraries. That is, that only includes code for the workloads you run. So you don't need to like recompile the shared library or do something else.
I see. Okay, thank you. I think I can follow up on linking. Thank you.
One kind of maybe basic question. Who would be the user of negative ML? Would it be the framework vendor? Would it be the vendor that incorporates PyTorch in their product? Or would it be an end user running their particular model that would want to shrink it down? Does that question make sense to you?
So
Have you heard the question?
Yeah, who's the user of negative ML, right?
Is the question where do we see the
Who gets the most benefit,
used?
right?
Who is the expected user of negative YAML? Is the
Okay.
firmware developer, the end user, the company who is packaging or using PyTorch in their products?
My thinking is that firstly the end users, the library end user, the framework end users. Another thing I can think of is that like cloud providers who provide like a serverless platforms, serverless function platforms that allow users to upload their own serverless functions. In that case, serverless functions usually they tend to be quite well defined and straightforward, which is a good use case for this runtime-based deep bloating. And also, for cloud providers or the serverless platform providers, they don't have the access to the. They cannot like ask users to like recompile your code using another framework or recompile your code using or compile your code using the framework you need to compile from the source code. I would say this is kind of a use case that the serverless platform provider, they can utilize this to kind of optimize the serverless functions that are uploaded by the platform users. Yeah, but basically, generally speaking, I would say this is used for more applicable for the end users of frameworks.
Okay, thank you.
Huafeng, I send you a connection on linking. I want to follow up with you on linking. So Yifei, thank you.
Yeah, there is a person interested sent you a request, so try to respond ASAP.
Sorry?
There is a gentleman here mentioned he sent you a question or request?
I just sent a
Connection or request on LinkedIn.
Okay, got it. Okay, thank you.
You got some followers. Thank you.
Thank you.